All right. So just as a quick review on plotting, give me a shirt color, please. Don't look back. Purple color.
Black.
Black. All right. So first person over their top row. So if I wanted to plot function in Matlab, let's say sine of x, okay? What would I do? What do I need to create to plot a function? So when I do matrix while close array, first I need an array of points, right? And those points should have both x and y coordinate in order to be able to plot. So if it's a sine function, what is a good choice for my x coordinates? What is the range that I should plot on? 0 to pi or 2 pi maybe, right? It's a sine function, right? So how do you want to create those? How do I create an array of equally spaced points? So I could use linspace. So I'm going to say linspace. And Matlab is nice enough to have pi already. It's really pi, so I'm going to put 2 times pi. Okay? And if I don't, yes? Good man. All right, let me say diary. So if you want to record this session, you can put diary, lecture 2, plotting, and date. So this starts a diary, and it's going to record everything that I type in, including the results. Okay? So it's really, that's what it is. It's a diary. And then I'm going to continue. So I can say how many points, or if I don't do it, it's just going to do 100 by default and create this x. So then in order to, I can either say y equals to sine of x, which will simply compute sine of all of these points, or I can just simply say plot x sine of x. Okay? And that indeed is a sine function. Now if I want to fix it up, I can say set GCA, if I want to fix it up after the fact, set GCA font size 16, it will increase the font size you see here. And for some reason it's not doing it by default anymore for me. So that way actually everybody can read the plot. Could go even bigger. Okay.
What does GCA represent?
GCA represents the current handle to axes. So these axes are GCA. So it's whatever is the current one. We'll get to that, but essentially I could have also typed it in, into plot command directly and assigned it there. But there are certain terms like GCF is the current figure, GCA is the current axis that you can then use to modify the current axis. You can also click, so there's a number of commands up there. I tend not to teach those you can investigate yourself because you can't really say on the exam, you can't say click on this and that, you actually have to be able to write the command. Also, if you know how to write the command, you can automate the process and you can remember it and execute it next day when you have the list of commands. Okay. So it's useful to know the commands. All right, so what we will do today, we will actually learn how to do multiple plots. So if I actually wanted to compare multiple different things on the same plot and create sort of a composed plot, I can use subplot. So there's quite a bit, so there's actually here 4 subplots, and we're going to take a look in the moment what they're doing. They're all plotting something related to sine. So one of them is plotting sine x, the other one is plotting sine 2x, sine 3x, and sine 4x. Okay? And they're giving some, what the what the axis should be and also the title, okay? And what this is actually going to arrange, it's going to arrange 4 plots on one, okay? And they're gonna be in a 2 by 2 arrangement, okay? So first in a 2 by 2 is this, second is this, third is this, so they're in a 2 by 2 and you just specify what 4 of them should be. End result is the following, okay? So give it a try. So x is essentially the same. So I'm gonna actually delete this figure that I want. If you want to delete figures from the command line, you can just say clear all, and it's gonna, or close all rather. Okay, so I'm gonna say subplot 2, 2, 1. So that's my first subplot, and then I'm gonna just re-execute this plot, and I can add those axes to be 0 to pi. I'm actually gonna put -1 and 1. No need to go 1.5. And I'm gonna say title sine of x. So you can actually now see this plot. And I'm just gonna repeat and keep adding one by one. So my second subplot, subplot 2, I'm gonna do the same thing except that I'm gonna put a different function, 2 times x and 2 times. Okay. And then I'm gonna do another subplot, 2 to 3. And I'm gonna do 3x and final one, fourth one will be 4. So these are the plots. Now, I keep saying something about executing. Yes?
When you type subplot, what are the numbers after that mean?
So 2, 2 means that it's a 2 by 2 arrangement. So, and 4 is which one in that arrangement. So it goes by 1, 2, 3, 4.
Okay.
So row by row, fill them in. Yes.
What's the title of what?
Title is sine of 2x, 1x. Here we go.
Thank you.
Or whatever you want to be the title. Could be pretty number 1, pretty number 2, pretty number 3, pretty number 4, something. Okay. Now, why is this important? Often you actually have, so let's say that you have production from multiple locations, and maybe there is too many of them to put on one plot. Okay, so it would be, but you still want them to compare. You often have to compare what is something versus the other. Then it's important to think for things to be lined up and to have axes between the same. So here I put -1 to 1. If you want to compare the plots and they're plotting the same thing, you should have same axes on all of the subplots so you can actually visually compare. Otherwise you can make wrong decisions. Okay? Or put things on one plot if it's not too messy. Okay? So this is just an option to have different plots. Now I keep saying something about re-executing things, and diary will line up what we did, but it's not, you can't easily execute the diary. So let's actually do that for one of them. We're going to get into that a little more, but I'm actually going to store all of these. I'm going to copy them here, and I'm going to say new script. Okay?
and I'm going to copy all of the commands that I did into that script. Okay? And I'm going to just remove these first two, and I'm just going to do the subplots. Okay? And I'm going to say save as, and I'm just going to put, well, subplot script. Okay? This is actually now stored as a subplot script.m. It is right here. Okay. So I saved it as a subplot. So you go to new script, and then you save as subplot underscore script. Okay. So now if I close or delete everything, I can execute it again. How? By calling it by name. And I'm going to clear everything. I'm going to close everything. Okay. So now I don't have X anymore in my workspace, you will notice. So if I say subplot script, I have executed it again. The entire sequence of commands. So it's simply a script of all of the commands that I executed that can be done again. And this is the key thing in programming. Saving your work and being able to automatically redo or possibly change something. You come back and say, well, no, I don't like -1,1. I can go to the script and change all of these to be from -1.5 to 1.5 and then execute again. Okay? Makes it much easier than typing things one by one.
Is clear all through the diary also?
No. No. It's going to be written in the diary.
Can you explain one more time how to save it as a script?
So you open, so whatever commands or whatever it is that you want to save, you just say new, you say script, okay? There is a new one. And I can say display, hello, okay? And then I can say save as, and I'm going to call this display script or hello script, how's that? Okay? So now it's saved as hello.m, and it's right here, okay? And when I say hello, it's going to execute it. It displays hello. It's that profound. Okay?
So we go.
So this is just a way to display things nicely. All right.
Professor, you
So,
type so fast.
you can see years of programming. Oh, yeah. And everybody's like, wait, what did you do?
After you highlight,
Slow me down, slow me down. What's the question?
after you highlighted it, what did you do?
Highlighted it?
Yeah.
That was for copying.
Oh,
So when I highlight, I copy and I pasted it into the. That's not copy paste, just like you would in any Word document.
copy paste.
So this is an editor, okay? So editor behaves as an editor would. There's a cut, copy, paste commands. So what I was doing here, I was highlighting things. Let's say that I wanted to do this, right?
Yeah.
So I did copy command, Control C.
How did you open the editor?
I said new script. So I can open a new one.
Say
So if you're typically working on something, something real, would you do it in the command window and save it as a script, or do you just write it out as a script?
Depends. I actually, if I'm just like testing things out, I literally do what I did here. I first type everything in, figure out that it works, and then I copy it, and then I work from that script. Right? So that initial test, I just type in. But you can also just start here, and then you would save this as so I'm gonna leave it to you so test, okay? Oh, apparently I already named something, test 1, okay? So you would type something here saying y is linspace between 0, 1 and plot y and y times 4. I don't know, I'm coming up with things. Then you save it, and the way I would execute it to see whether it works is I would just say test 1. Okay. Oh, did I plot? Plot can sometimes sneak into a plot behind here. So it plotted. This is an interesting test right here. That last subplot was the active plot, and that's where it threw my plot. Okay. So if I close this and re-execute test 1, it's gonna plot. So then you can keep fixing things, executing, however you feel like working, really. But it is important to ultimately save your work. Okay? And then, because often you're gonna make mistakes, so you have to weed out mistakes as you go.
Professor,
Okay.
is the only way to solve to save your code, or you can save it from the command, or is it like that?
Diary you can open up and then you can grab those commands and save them as commands that could be executed. Diary in itself you cannot execute. You do not call test 1 and execute.
Okay.
So with a script you're sort of creating a function of sorts that will just execute all of those commands.
Oh, okay.
Diary is just a diary, it's just a text file.
Okay. All right. Okay, so let's now move on to some cooler plotting. Okay.
So I believe this is something that you plotted or graphed as part of that tutorial, if you remember. Okay. So now we're actually going to dissect it. What does it mean? So one thing that I have to understand is that, again, plotting requires points. Having all of those, or at least a good mesh of points defined that you can plot. So this plot, and I'm gonna get into the details in a second, what it really creates for each of the points that I'm plotting on this surface, this point, this point, this point, this point, this point, I need X, Y, and Z. Okay?
So essentially I have to get myself X, Y, and Z for each of these points.
So first thing that is done, okay, if I look at these values here below,
Okay, this point has X value minus 2 and Y value minus 2. Okay, so this is minus 2 minus 2, minus 1 minus 2, 0 minus 2, 1 minus 2, and 2 minus 2. Does everybody agree in terms of X, Y? Then the next row, okay, is minus 2 minus 1, minus 1 minus 1, 0 minus 1, 1 minus 1, 2 minus 1. Okay, and I keep going. So I have sort of a table of these pairs. Okay? And so I have a table of X's and I have a table of corresponding Y's. A matrix of X's and matrix of Y's. Okay? So essentially, this is precisely what MeshGrid is doing. Okay? So here, well, actually I have more points here along, but we could actually just create, so let's just do that. So if I do minus 2 with space 1 to 2, okay, this array is minus 2, minus 1, 0, 1, 2. Okay? You all know what this means? Start at minus 2, have a spaced 1, and create an array of points spaced like this. So basically, let's actually create a little coarser mesh than on this slide. X, Y, okay, is mesh grid of, I'm going to say minus 2 space 1 to 2 and minus 2 space 1 to 2.
So when I do that, this command meshgrid will give me two matrices. One is X, one is Y. And those two matrices will have all that is enough to create those points that have both X and Y value in these required ranges.
Take a look. So basically, I have two matrices. Okay.
So basically when I combine x coordinate and y coordinate, I'm going to go -2, -2, -1, -2, 0, -2, 1, -2, 2, -2. Those are all of the points on that line that I was pointing. And then I go to the next row, it's -2, -1, -1, -1, 0, -1, 1, -1, 2, -2. Okay? So if I grab from specific position an x and y from these matrices, I'm going to get this full description of all of those points in the plane. Okay? And then I need to compute z for all of them. Okay? So for all of those corresponding x and y values, okay, I'm going to compute z, and I'm going to use vectorization for that. Okay? So I know that if I have just x and y value, let's say that -2, -2, okay? Then I could just say x times exponential of -x squared minus y squared. If I have a scalar, I know how to compute that. Okay? Good news is that we have vectorization in Matlab, so I can actually operate on all of those matrices, and with one command, compute all of the z's that I need. Okay? And that is this dot operator here. Okay? So this dot operator will take every element of matrix X and multiply it with exponential of corresponding -x squared minus y squared. Okay? So I can just operate on an entire matrix, which is really cool. Okay, it shortens writing a lot. But you're telling Matlab, okay, for all of the matrix elements, create me another matrix that has element by element this computation. So let's do it.
So my z is going to be a matrix is x multiply, and I got to put a dot so that it goes element by element, exponential of minus, again, element y square
-1.
minus y square.
Oh.
So this is a matrix as promised. Let me execute it again. So this is a matrix.
And you can see where x was 0, all of the corresponding elements are 0. So
I'm sorry.
Go ahead.
What is it? Dot again?
So dot operator will actually then take first, so basically this z of 1, 1, okay, is x of 1, 1 times exponential of minus x of 1, 1 square minus y of 1, 1 square. Then this z of 5, 5, okay, this is z of 5, 5, is x of 5, 5, let's actually do that, x of 5, 5, that's just a number, right? X of 5, 5 times exponential of minus x of 5, 5 square minus y of 5, 5 square is 6.7 times 10 to the minus 4. When you actually round that up, you would print 0.007. Okay? And that number is sitting there. We're just printing only first 5. Does that make sense? So it's going to just grab every element, but it's an elegant way to just compute it all at once. The homework, has homework been posted? Have you posted homework? Okay, so it's going to be posted by the end of the day. You will actually do this, so I'm going to give you a porosity field in 3D, and you're going to compute or projected permeability for all of those points. Okay? All at once. And on a large, it was 70 by 70 by 120 or something like that. A lot of points. Okay? So it saves a lot that you don't have to type this in. With 5 by 5, you would survive typing things in, but anything larger. Okay, so now I actually have all of the points that I need to plot. Okay? So here I needed for -2 and -2, now I have a corresponding z. Okay? Then -2
-1, -2, I have a corresponding z and so forth. I can plot all of those x, y, z's. And Matlab is nice enough to mesh this surface for me once I just give it points. And that command is called surf. So you can just do surf x, y, z. And here it's very rough because my spacing was rather rough. I wanted to be able to print 5 by 5 matrices, okay? But knowing that we can automate the process, I'm gonna re-execute this, okay? So I'm gonna say, okay, I'm gonna redo that command doing mesh grid, and I'm just gonna do a little better spacing, 0.2. Oops, so this is now larger. And my z, I'm just gonna re-execute it again. And I'm gonna just do surf of x, y, z. So this is just refining and making larger arrays so I have a smoother surface. Yes? Just close it. Close it and redo it again. If your surface went to that subplot, close the subplots. And the surface went somewhere. Here we go. This is a smoother one. Okay. Now something that you can do color map gray. You can do color map. Which ones do I remember? Jet. You can do color map. How many of them do I know? Let's actually see. Let's actually see color map here. So this will actually give you a color bar of values. And I'm trying to figure out what other color maps. So if I do help color map, I might get some other different maps. So if you go on Matlab web page, you can find all kinds of color maps. So my next black shirt, you're gonna have to go to the color map here. Jet I just did, something else. Shall we try summer? Still summer here. Let's try summer. So I'm just gonna say color map summer. And here we go. Summer is green in many places other than Austin. It's kind of yellowish. Okay? Alright. So you can modify this plot in various ways. So, basic process that I told you, we'll plot any function z that is function of x and y. But you could also just have a matrix of data z that you could plot, and you could assign what x and y values mean that way. Okay? So you can plot it. And then there are different types. I showed you surf. You can just type in mesh instead, or mesh C, or surf C, or surf 1. And you can actually take a look how it executes. Here's the difference. Okay? So you have mesh plot right here. This is a surf plot that we just did. Surf C is also going to get contours of the data underneath. And surf L plot is going to do this. Okay? Not sure what the difference is. You could also use it in a number of ways. So if you don't give it any x and y's, if you just have a matrix Z that you're gonna plot, it's just gonna take those z's as elevations, okay? And it's gonna assign x and y's from 1 to however many points you have. That could work, okay? So if I just did that,
let's do that quickly. I'm gonna close all of the plots I have. So I'm just gonna say surf of Z. Okay? Then you can see that these points here actually go between 0 and 25. So it's just gonna
assign
numbers, however much data you have. Sometimes if you want to rotate the plot, by the way, there's here rotation. And then you use the mouse to rotate if it works. There we go.
Wow.
Okay, so this is a top view. This is a side view. So I'm holding a mouse. Okay. So this, just like in anything else, I could say X label. So first I'm gonna say that set GCA to 16, so it's a little larger. But I can also say X label, X, Y label, Y, and Z label. So just like you have X label and Z label, you can do Z label. Okay, so now you can see X, Y, and if I rotate around, it labeled Z as well. Okay, so you can play with it. You can give it a title. Pretty surface. Okay.
well, I don't have physical meaning for it, so. Any other suggestions? Right, it's kind of like,
Back, to like the original, after you rotated and all that stuff, you can get it back.
can I get it back? Actually, one of the,
Sometimes there's a shortcut key to get it back here, but not other than, apparently not. Here and there, some of the software actually have shortcut keys for some,
but you can always replot it, close it, replot it again.
Hey,
and then let's just quickly look at what would mesh do. So if I say mesh, I'm going to get sort of like just a wireframe. All right. So let's just briefly review what is being done here. So in all of these surface plots, what you have is a matrix of values. So here Z11, Z12 all the way. So Z and M, however many. And what Matlab does is takes those Z's as elevations and plots a surface corresponding to those elevations. If you provide it a matrix of X's and Y's that also have to be of the same size, then it's going to plot X, Y on the proper scale and also those Z's. If you don't provide it with X and Y's, it's going to plot just numbers, however many. So numbers up to N and N, okay? So this is again why matrices are important. A lot of data will come like this. You are going to have, this reminds you of like some sort of plots of elevation, right? In petroleum engineering, you're going to have depth, okay? So a lot of basically geological description of your reservoir will actually come as plot of where is your top surface of a reservoir, for instance, okay? So in that sense, you might want to plot those. Okay. So essentially, we learned how to take a vector values x and vector values y and combine them to actually plot x, y's, and z's. So my point z of ij corresponds to ith value of vector x and jth value of vector j. Okay. So then I need to actually have those points x, y, z's in order to plot them, and this is just a generalized view of what we did. All right. So these are the example plots that you can plot with, and you're going to have an example.
Another important thing is contours, and in petroleum engineering, you're actually gonna have contours at a constant depth in a reservoir, what's happening, right? So often when you go hiking, you're gonna get a map in your favorite park, right? And you're gonna see contours that are noting what is the elevation. In petroleum engineering, you get the same, just flip it down, so it's gonna be depth, okay? But essentially, what those contour lines tell you is that as you're walking around the contour, you're not changing your either elevation or depth, okay? So if you're a lazy hiker, you're gonna pick a contour and just walk down that contour so you're not going up or down, okay? If you see a lot of contours bunched up, they're kind of dense, that means that I'm changing elevation quickly because contours are typically plot at a constant interval, so let's say every 100 meters, okay? So if a lot of contours that are 100, 200, 300 are close by, that means I'm changing my elevation really quickly, so avoid those areas if you're hiking, okay? And in petroleum engineering, that might mean that you're actually on a fold, okay? So there are a lot of contours that are bunching up. So if you want to plot that type, you can just contour your z data, so it's going to create those lines of constant elevation z for you. And we can actually do that here. So let's just do, I'm going to kill this plot. If I contour z, these are essentially contours. If you put this, you can either click on this to get a color bar, or let me actually redo it by doing commands. So say contour z, then I'm gonna set my GCAs to actually have something visible, and I'm gonna say color bar, and that's gonna add the color bar. So if you look at this yellow that is close to 0.4, this is the values where I had 0.4. So these are all of the values that are close to 0.3 right here. Okay? All of the values close to 0 are right here, and so forth. Is that really true? I'm going to plot another figure. So just type figure to have two separate plots. And I'm going to do surf of z on that plot. And also color set and color bar. So indeed, all of those, so if I walk here, this is corresponding value, right? Then I'm not going to change elevation, right? I'm here on the constant, right? That's this line right here, is this. And if you're wondering, oh, why am I looking at this plot? Why am I not looking at the same plot for this? I can actually create third figure. And I can just say surf C, surf and contour of Z. And I'm going to get both. C. Okay. So you can see this corresponding contour is right here. So often what you will actually see is these contour plots because they're easier to monitor in 2D. So it's a projection of sorts. Yes.
After surf C, did you do set and then
Surf
color
C
bar?
of Z, and I did set of GCA just to have large numbers here.
Oh.
That's what I'm doing it for, so you can all read.
And then
Otherwise,
color
I'm the only one who can read these numbers.
bar. And then figure again, color bar.
So if you do figure is going to start plotting a separate figure. So that they are not all going on the same one. So if I don't want to delete the previous figure, by whatever it is that I'm plotting again, I'm going to do figure as a separate figure, and then surf C. So those are some options in 3D plotting. You're going to have a lot of fun
even if it's a little frustrating at the beginning with the homework, because there will be a lot of plotting like this. But again, it's going to be reservoir data. So initially, when you try things out, it has to be a little frustrating.
Could you change the amount of levels that it makes?
Yes, you can. So you do help and contour and find out. Help, contour. Okay? Yes.
Is there a subsurface like subplot?
You can put whatever you want in subplot. Yeah.
Subplot 3D.
Good question. So let's do this. I'm going to close all figures. Subplot 221. And then say surf of Z. Then subplot 222 and say mesh of Z.
How do you choose those coordinates for the subplot? Like,
2 means 2 by 2 arrangement.
okay.
First, second, third, and so forth. 3. Whoops, hi. Yes, what did I put? Oh yeah, I meant subplot. What is else there? Contour of Z. And subplot 2 to 4. What's left? Mesh C of Z. These are all of the options. And I just figure, there we go. Throw in whatever you want. So he doesn't care what you're plotting. Okay? You're just saying in subplot, just create 4 at once and go with it. Oops. All right. And guess what? This is how this plot was created. Right? So you can modify them all as you'd like. Okay. All right. So those are contour plots. So this is one way to actually have C label to label. You can do C label and then it's going to label your contours. And you can change the color map. There's a cool color map and so forth. So just to wrap up this plotting exercise, this is actually some interesting stuff from my research. This is a fracture from a tight gas field that is very deep, 10,000 feet below. 10,000 feet below, the matrix here, this is rock matrix, is very tight and it's mostly cemented completely. There's nearly no porosity. Okay? The only porosity I have is in these fractures, and they're kind of propped by quartz. These are quartz crystals growing up. And crystal growth is kind of random. You get a seed that goes in this direction, you get a seed that's going in that direction. And sometimes they actually prop to the other side, sometimes they don't. You can see them here. So when I actually x-ray this fracture, I get sort of, this is my, what's called aperture is the distance between, okay? So this aperture field is typically with respect to the midplane. Like I look at this aperture, the distance, okay? And I can plot it. So you can actually see this is the three-dimensional surface around this fracture. I mean, it's very tight. This is all of the space that is left. If I'm moving through this, so I can kind of very constricted in my movement. And when I plot the aperture field, this is how it looks like. So a lot of times it's 0. That's where I have these crystals growing across. Okay? And this is where I have open space. So aperture field is one example in research that you would plot using. So this is essentially plot by surf. I'm now forgetting what, but there's actually those black lines are missing because it's actually really large mesh. There was 700 or so points on each side. So there is a way to modify surf to avoid those black lines that mesh. Okay? So when you have a lot of points, then you get a plot like this. And then I use it as a color bar. So this is this aperture in millimeters. So you can see that I go up to 1 millimeter. So that's really small. But again, that's the largest pathway you have through these fractures. And these are natural fractures. So if you have a network of those,
You have to know where they are because they're gonna fill your woods wherever it is that you're. But they could also enhance your production. So if you're fracturing this reservoir, this natural fracture network could help you reduce the reservoir. Okay? So mapping out fractures is something that is often done and important knowledge. So again, as you get the data that is interesting, you're gonna decide how to use all of these functions. One more example. This is fluid invading this model reservoir, so this is gas going into water. So this is done with contour.
And that's also Matlab?
Yeah, this is in Matlab. With contour and contour.
You sell that as one or not, you just probably get like a
It's actually part of my freely available